This is the conversation with Dr. Brian Keating. He is a cosmologist, astrophysicist, the author of acclaimed books like Into the Impossible and Losing the Nobel Prize, host of the Into the Impossible podcast, and the Chancellor's Distinguished Professor of Physics at the University of California, San Diego. In this conversation, we talk about the mysteries and the magic and the wonder of the universe, the challenges of tackling big existential questions. We talk about the Big Bang, cosmic inflation, the cosmic microwave, background radiation, the BICEP and POLARBEAR experiments. And then we also talk about the problems with this small, little-known prize known as the Nobel Prize. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars on Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, please consider making a donation on Patreon or Anchor. You can buy super thanks on YouTube. You can join as a member on YouTube, or you can buy gifts on Instagram Reels. If not through monetary channels, and do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally.
And now it's no time.
In the movie Annie Hall, a young Woody Allen is taken to the doctor by his mother because he refuses to do his homework. And upon being asked why he refuses to do his homework, he says, the universe is expanding. The universe is everything. And if it is expanding, someday it will break apart, and that will be the end of everything. You got a telescope, your first telescope, when you were roughly the same age as Alvy, Woody Allen's character in that movie. And right from that age, you've spent a life studying the universe, the origins of the universe, cosmology, and the potential demise of the universe. Is there a way to study the universe and tackle these big, impossible questions without inculcating these feelings of nihilism and existential dread like Alvy? Is there a way to study the universe and keep that same wonder and awe that you have maintained for all these years? I guess another way of phrasing this question is, after you discovered that the universe is going to end, how did you continue doing your homework?
Well, you know, the punchline of that scene from Annie Hall, I don't think we can spoil it. You know, it's 50 years old movie, so I don't think it can be spoiled at this point. It's too late if you haven't seen it. His mother hits him upside the head and says, you idiot, you know, you're in Brooklyn and Brooklyn's not expanding, which is actually true. It's 100% correct. Brooklyn is not expanding. Our solar system is not expanding. Our galaxy is not expanding, and even our local supercluster of galaxies is not expanding either. So she's absolutely right. And if you look at it in those terms, what is there to worry about? There are many, many things to obsess about, to concern oneself about, even as a professional cosmologist, rather than the end of the universe. Which I shouldn't say that we know for sure that it will, you know, expand forever, you know, rip apart, heat death. We actually don't know that. And to say, you know, that we're confident in how the universe will end, whether in fire or in ice, the two different, you know, seeming contradictory outcomes of the universe, is really to presuppose and edit out the ability for scientists like me and my colleagues to do the research that we're doing. So if we knew the answer, it would be a lot less satisfying. And I think that would be more depressing, if you will, than either of the scenarios that Alvy envisioned. So for me, it doesn't affect me at all. Obviously, the timescales are so long. I've lately been writing about this proposal by a British productivity expert named Oliver Burkeman, who has this concept called the cosmic insignificance therapy, which is basically, you know, you and I are pretty small compared to Jupiter, and therefore we shouldn't take ourselves too seriously. I kind of feel like that's nonsensical, to be honest. Not to, you know, be too insulting of Oliver's work, but basically the notion that, you know, size determines importance. I point out, you know, there was a virus called the COVID, virus that took over the world. It's barely a few angstroms, you know, in diameter. Certainly, we're much larger than that. Was that not significant to us? I mean, of course not. It devastated life on Earth. The lockdowns did, at least. And so from that perspective, I think thinking about things in terms of what matters is their size leads to a great deal of kind of stupid thinking. And it tends to give comfort and solace to people who like Berkman, who I assume is an atheist, or your past guest Lawrence Krauss, maybe, or folks like that. But actually, I find no solace in that, nor do I find anything troubling about it. I think it accentuates the fact that human beings are the only entities that we know about that can contemplate the origin of the universe, the end of the universe, and more immediately, these things could not happen for a trillion years, perhaps, in the case of the heat death of the universe. So we can contemplate the fact that we're around for 70, maybe 80 years if we're lucky. And that's much more significant, and making that time count than thinking about, these kind of existential dread considerations that Alvey and many others like Berkman might suffer from.
You started contemplating these questions at a very young age, which is rare. Arthur C. Clarke had once said that the only way of discovering the limits of the possible is to venture a little bit past them into the impossible. As the author of the book Into the Impossible and the host of the podcast with the same name, I'm sure you've heard this quote before. You have been fascinated with these big questions from a very young age, and you've said in previous interviews that engineering didn't excite me as much as these big questions. And I want to dig into the why. Why do you think you were inherently drawn to these big questions? Kids your age, when they pick up a telescope, they don't feel the same way that you felt at that age. So why do you think you were drawn to these big, tough questions?
Yeah, on my website, I have a guide to getting your first telescope. This is not much bigger than the telescope that I had as a 12-year-old, or that Galileo himself used, 400 years ago exactly this week, to discover the moons of Jupiter, which was supporting evidence. It didn't prove it, but it supported the claim that the Earth was not the center of the solar system, or the universe as it was known at the time. And I point out, you can get this at briankeating.com/telescope. And I point out, when you get a telescope, you can actually not only see the things that these great minds that inspired me, years ago, decades ago, but you can feel what they felt hundreds of years ago. In other words, when Galileo made the sketches of the moon's phases and saw that it wasn't perfect and crystalline and smooth, it had these mountains and craters on it, he realized he was looking at another world, not just some fanciful orb that floated around in the heavens, never to be understood or comprehended. So you can do that only, I think, with a telescope. There's no other instrument. You can't, use your own Hadron Collider. You can't use your own James Webb Space Telescope. But a tiny little telescope, you could not only see what they saw, but feel what they felt. And that's what's so important. So that's really my entree into astronomy. It wasn't podcasting didn't exist, 30, 40 years ago when I got into astronomy. So for me, it was the notion of doing research. And when I awoke one night to see the moon outside and a bright star next to it, I became fascinated with what I was looking at, but I couldn't get the answer. I had to delay the gratification because, Google wouldn't exist for another 16 years or so from that point in the mid-1980s. What I had to do is kind of wait and go to the library and get the New York Times and look around and see what was that object next to the moon that seemed to rival it in terms of its brilliance. And it turned out to be the planet Jupiter. So I had actually done the exact thing that Galileo did. I ended up getting a telescope just like this small one I showed you, and looking at the moon and seeing the craters, and then seeing the moons around the planet Jupiter. And imagine that. You could see immediately quintupled the number of moons I had seen in my life in one instant. And where I differ from Galileo, obviously, I didn't realize it for the first time, but it felt like the first time. And that's what's so unique and delightful about astronomy, is that you can feel viscerally what the greats of history felt in no other way. There's no other, real way to feel like that. Darwin's theory of evolution, you don't really come to that. There's no instrument that led him to this. It was sort of explorations and thinking about and meditating on these issues. So that's what's so wonderful and unique about it. And that's why I love to share the journey with the listeners and viewers on your channel, my channel. And it's something that we can do that I always look at, well, what could I do? What are the biggest questions, as I said, in that quote that you mentioned? And that's, I always like to think about, what could I do that, like, Steve Jobs can't do, because he's dead, or one of my heroes, Carl Sagan. Here's a puppet of Carl Sagan here. So they never had podcasts. They had books, and I love to repay sort of the debt of gratitude that I have to great authors like Carl Sagan and Isaac Asimov. But the fact is, more people don't really read books as much. Their attention span is down. More people, one of every two people listens to a podcast basically on a daily basis now. And it's really changed and transformed how we receive information and news and vote for politicians like Donald Trump. You know, it really transforms things. So for me, the podcast and going on other people's podcasts like yours is a way to kind of share the love that I have of the universe and make it accessible to people who aren't professionals, who will never be professionals, but want to keep the fire of curiosity burning bright. And I love to be able to do that. And it's a great privilege to me. So I would rather be talking about that than, some hot sauce that goes on wings, or some true crime story in Los Angeles. There are many more popular podcasts than mine, and it'll always be like that. But the niche that I've kind of developed is communicating with the public on one hand, asking them to ask questions of guests that I have, from Neil deGrasse Tyson to Lawrence Krauss as you had, and I've got many more great intellects coming up this year. It's going to be the biggest year for me. So being able to engage the audience, ask them to ask questions of these people they'd never, ever get the chance to talk to otherwise is a great thrill and a privilege and really, quite frankly, an honor to be able to do it. So those are the kind of things that motivate me outside of my research, obviously, which is to uncover how did the universe begin.
One more question before we start talking about your research. Obviously, you spoke about the telescope and how powerful it is as an instrument. You often say that the only prescription Dr. Keating makes is to get your child a telescope. And I think it's in line perfectly with something your English teacher, Mrs. Tompkins, used to say, that education is not pouring in, but bringing it out. And I feel like the telescope is such a powerful instrument for actually bringing it out than pouring it in. In the Talmud, there's a verse that says, you may speculate from the day that days were created, but you may not speculate on what was before that. Do you think we'll ever be able to find the answer to the question, what was there before the universe began? Do you think there's light at the end of the tunnel, so to speak? Or do you think the only hope we have is to try and get as close as possible to the answer, inch closer and closer every single day, but we'll never really be able to find out what was there before days were created?
Well, that's a very, very difficult question to answer, definitively. And the reason is because if indeed the universe began and time itself began at a moment, which we don't know for sure, and that's part of our research, is to determine whether or not that is possible. And if it did occur in that way, where time itself came into existence, how can you measure the evolution of events? I mean, we think about time as what allows us to separate one event from another event in four-dimensional so-called space-time. But if time itself comes about at a specific moment, there's no left-hand side of the number line. There's no before to ask the question about what changed. What is the underlying independent variable that allows the evolution, the size of the universe, say, or the density of the universe, or the temperature of the universe? How could that change from nothing, from where the concept of time didn't even exist? As many eminent scientists, including Stephen Hawking, believe that to say what happened on the Tuesday before the Big Bang was a nonsensical question akin to asking what's north of the North Pole. And nowadays we do ask those questions because in many cosmological models, not the ones that Stephen Hawking preferred perhaps, but in many models, the universe does have an origin in time. And in many other models, it has a cyclical nature, meaning that the universe evolved from one state to the current expansion of our current observable universe. That's how we speak about it. What can we see? What in principle is possible to see via light, which travels at the fastest speed possible? And the question is, in those models, there's a very sensible notion of what happened on the Tuesday before the Big Bang, where the Big Bang doesn't mean and has never only meant some singularity, before which time didn't exist. So I think Hawking was wrong on that count. I would have said it to his face. I only met him once about 30 years ago, and he could barely respond to questions. I did love to ask him, a question at the time. I didn't have the courage to do so. So always take the chance while you have it. So, but the real concept that we're trying to wrangle out of the data, not just speculation as he was doing, is was there a singular moment or was there not? And if there wasn't, then what was the universe like before our current universe? And ultimately, perhaps, are there other universes? Are there universes besides ours, whether in space or in time, that pre-existed ours in a cycle, or that are parallel to ours in either a multiverse or in sort of Everettian many worlds sense? And these are the most fascinating questions I can imagine investigating. And that's what exactly I've orchestrated my research to be oriented around.
I think this is the perfect opportunity to start diving deeper into your research. We spoke about the multiple theories that exist of what happened before the Big Bang. Let's start with a set of silly questions. I know you've answered this in detail before, but I would love a quick refresher because I think it would set the context for all the other questions to follow. So very quickly then, what is the Big Bang? What happened right after the Big Bang? And what is the cosmic microwave background radiation?
So, the cosmic microwave background radiation is, I always joke that's how I pay the mortgage around here, because the cosmic microwave background taps into our most primal instincts as human beings, not just as scientists, which is that we interpret the world primarily by what we see. Doesn't mean if you're blind you can't interpret it, but let's ignore that. That's an edge case. Let's talk about human beings. So we're born with two refracting lens-based telescopes in our skulls. Here, if you're listening at home, I'm holding up the telescope again, which has a lens in it. Our eyes have one lens as opposed to the telescope, which has two. That's immaterial. And in the case of the telescopes that we build, we're not looking for optical light in the visible portion of the electromagnetic wavelength, because that's not where the signal that we're looking for resides. Instead, we're looking for heat, because we're looking for the aftermath of the explosive origin of our observable universe. And if that universe had a so-called singularity or a beginning point where in time itself began, it will have very different optical characteristics to a universe that had a cyclical origin. And we can reveal those properties by looking at a property of light, which is very unknown to most people. It's called polarization. So light always has three different properties, two of which are very familiar. The intensity, how bright is this spotlight right over here? That's how intense, how many the photons are and how much energy they have. And then the color is related to the energy, but is really called the spectrum. What is the breakdown by frequency or wavelength of the light that we're receiving? And both of those properties hold true for any electromagnetic wave, from a radio wave to an X-ray. But there's a third property called polarization, which is the orientation of the electric field of the light, what plane it's residing in, or if it has no polarization. It may not have any discernible direction whatsoever. And polarization is kind of like if you and I were to hold a rope. I don't know, where are you right now? Where are you located?
New York City.
So you're in New York City, close to my own old hometown.
Yeah.
So if I shook a rope between you and I, and this was out there, whatever direction, up or down or left and right, that would be the plane at which the rope is polarized. And so too, light has polarization. But again, we're not talking about optical light. We're talking about the oldest light in the universe, called the cosmic microwave background. And this is the relic, the leftover heat. Whenever you make something, when you generate energy from coal or oil, you always have externalities, residuals, and things you don't want. Sometimes that's, carbon dioxide or whatever. But even in the case of nuclear power, which has no carbon dioxide as a byproduct, it still has excess heat that gets released and has to be then, dissipated to a lower temperature reservoir. So there's always an externality. Whenever energy is generated, whenever matter is generated, nuclear fusion, for example, there's an excess left over of heat. And that excess heat that's left over from the formation of the very first elements in the universe's history, namely hydrogen and helium and their isotopes, that has a leftover from that fusion process, a heat that was a result of the formation and the energy that existed before their production. That now has been stretched and cooled off from many, many millions of degrees above absolute zero to just a mere 2.7 degrees above absolute zero. And then upon that signal, we can look for how intense it is, as I said. We can look for its spectral characteristics, how much energy is there versus wavelength. But we can also look for its polarization. And specifically, we look for its polarization as a way to unravel whether or not the universe began with this inflationary singularity. So that it would be imprinted not on the color of the microwaves, if you will, not on the intensity of the microwaves, but exclusively on its polarization properties. So our telescopes from BICEP to the Simons Observatory are primarily concerned with mapping as a function of where you look on the sky, not how bright the microwaves are, not what their colors are, but what their polarization looks like.
We covered some really important definitions: Big Bang, cosmic microwave background radiation, cosmic inflation, and how the polarization of the cosmic microwave background radiation tells us about the inflation theory. You were part of the team that worked on these experiments, the BICEP experiments, or the background imaging of cosmic extragalactic polarization, rolls off the tongue completely. I want to talk about the science and engineering aspects of these experiments. How did you set up these experiments? What did you observe, and how did that confirm cosmic inflation?
Well, so I should stop right there and say it hasn't confirmed cosmic inflation.
Okay.
In fact, the title of my book, my first book, is called Losing the Nobel Prize. We would have won the Nobel Prize, and that's the only sense that we can really say we lost the Nobel Prize. So losing the Nobel Prize it's based on a telescope that I co-created, invented at the South Pole. So if you're watching, there's an image of it on the cover of my book. And that telescope was placed at the South Pole in order to effectively see if we could see this pattern of polarization. So this I started in the year 2000, so it's now in its 25th anniversary year. It's been upgraded just like your iPhone or Android gets updated every year to the latest, greatest model with more pixels and a better camera. We too have done that, or the team has done that, going from BICEP, the original one that I invented and built and installed at the South Pole, all the way up to BICEP, the fourth generation, which is called the BICEP Array, which I'm not involved with anymore, but very similar people, very similar science goals. And because we didn't confirm it, although we claimed originally that we did detect this signal, this imprimatur, the pattern that would be there inexorably only if and only if inflation took place. Now, we were mistaken. That's why it's called losing the Nobel Prize, not winning it. We actually saw, instead of seeing the effects of a singularity or the inflationary origin of the universe, which would be a radically explosive process that produced not only heat and light, but also waves of gravity, gravitational radiation. That's what produces the unique polarization pattern. We didn't see that. We saw instead these microscopic grains of dust, which are effectively like micrometeorites. And so I want to point out to your audience that on my website, briankeating.com/YT, you can go there and join the channel as well. But I do give away these meteorites to folks that join my mailing list, which you'll get information about my podcast, my guest, upcoming guest, and cool news about the universe, totally free. And I give away a lot of stuff on there. But if you have a .edu email address, if you're a student, I love you guys so much, and you live in the USA, I want to really make sure that you guarantee to get one of these little meteorites, these beautiful meteorites that I have here. But if you imagine, and that's if you go to briankeating.com/edu. Now, if you imagine these things shrunk down to the size of dust particles or iron particles, like filings in a magnetic field demonstration, that's actually what we have in the galaxy. See, this object this meteorite that I'm showing here, came from the explosive blowing up of a supernova long before our sun even existed. So these meteorites that I give away are about 4.5 billion years old. And they actually trace themselves, which is older than the age of the Earth. So they actually date to a pre-existing primordial solar system. And so on the one hand, we didn't expect these particles to create as big. We knew that they would be there. We just didn't think they'd be so pernicious and so exactly, impersonating of the signal that would be there if we saw the inflationary gravitational radiation. So these objects align in the Milky Way's magnetic field, just like the needle in a magnetic compass, an old-fashioned compass. The Milky Way has a magnetic field, our galaxy has a field, the Earth has a field, you and I have tiny magnetic fields, etc. It's very hard to get rid of magnetic fields, very hard to shield magnetic fields. If you have a piece of metal, you can make a Faraday cage so your phone won't get any signals, but you can't actually use that same Faraday cage to block out magnetic fields. If you put a compass inside of what do they call those little bags that, Faraday cages that people that are super paranoid about the government spying on them, they put their phones in every night, and they probably still don't sleep that well. But the magnetic fields in our galaxy are impossible to really screen out, and because of these materials are still floating around, not just in our solar system but in the entire galaxy as a whole, we were susceptible to seeing the orientation and polarization produced by them, and that's what was so, as I said, pernicious, because it exactly mimicked the signal we would see if inflation took place. So although the team, I wasn't invited to it, but had a big press conference at Harvard and made newspaper headlines on every major newspaper, CNN, MSNBC, Fox News, all the different, channels it was featured in. And yet we essentially made a mistake in our claim. We didn't blunder. We didn't I forgot to, my thumb was over the lens of the telescope. Or I didn't take the lens cap. We didn't make a stupid mistake. In fact, we measured more precisely than ever this signal from an astronomical source called, cosmic dust, particles of dust in our galaxy. And we still have, the team still has, the best constraints on the inflationary epoch that have ever been measured. We're trying to beat that now with my team on the Simons Observatory. And we hope to have our first data. We've already collected our first data set last year even. And we hope to actually release the data in the upcoming year or two. And that will be even more sensitive than the current record-holding BICEP experiment. So it's very important to realize it wasn't a blunder, it wasn't a mistake, it wasn't fraud, it wasn't p-hacking, but it was done in essentially the consequences of what's called confirmation bias, which is a very, very disturbing trend that all scientists can fall victim to, including myself, which is that you tend to want to see things like even you kind of mentioned or hinted at, maybe we did see it, or this is how did it confirm the inflation, and that's fine. I think a lot of people, even professional physicists, when they meet me, sometimes they're like, "Oh, you were part of the team that detected inflation," and I'm like, "Well, no, you obviously haven't read my book, or we didn't detect it. If we did, I'd be maybe having some share of a Nobel Prize." So the effect was so ingrained in both scientists' minds, but in civilization's minds, because it was so incredible and compared to the greatest discovery of all time, the detection of the Big Bang, that people still believe it's true. And that, again, is a symptom of confirmation bias. People do want to see what they want to see. It's very hard to dislodge the notion from their minds that their evidence might not be what they think it is.
Cosmic inflation is such a powerful theory, and there's definitely opposing camps with Alan Guth on one side, Paul Steinhardt on the other hand. I completely understand that aspect. You alluded to the newer experiments that you're working on. You alluded to the Simons Observatory, the Simons Array, and the POLARBEAR Experiments. I just want to quickly linger on the difference between the POLARBEAR Experiments and the BICEP Experiments. What are you now trying to observe with the POLARBEAR Experiments that you couldn't originally do with the BICEP Experiments?
Yeah, so the BICEP experiment was a refracting telescope. It was only about a 20 to 30 centimeter diameter lens. So this telescope is about 10 times smaller than it. So it wasn't a huge aperture. And in astronomy, the aperture of a telescope is proportional to, inversely proportional to how small an object you can see with it. So with a very, very big telescope like the James Webb telescope or the 30-meter telescope that we're trying to build here in California and elsewhere, that instrument will have, literally thousands and thousands of times more collecting area, because the area scales as the diameter squared. The cost of a telescope scales as the diameter cubed. So to build a telescope that collects twice as much light, you need to spend 8 times as much money. And so in the early 2000s or late 90s, I realized, well, we're actually looking for a signal, this polarization signal, unlike the temperature and the spectrum signal. It's a very large scale signal. It's very large on the sky, meaning you don't need a huge telescope. And so you could make a very cost-effective, portable, compact telescope that you could put somewhere that had very low contamination. Again, we're looking for heat, effectively for heat and the polarization of the waves of light, the radiation of that heat. So we want to go somewhere cold, and the South Pole is an ideal place to go. Also, the mountains of Chile, where the Simons Array, Simons Observatory, and POLARBEAR are located, is an outstanding place to be. We're above half of the atmospheric pressure that we feel at sea level here in New York or in California, where I am. So the trade-off is always between, how expensive would it be to go to space, which is incredibly expensive, prohibitively expensive in most cases, to build a telescope. We actually didn't need such a big one for doing BICEP. Now, for POLARBEAR, Simons Array, which are the same size telescopes, those are reflecting telescopes. Those see light from the bouncing off of radiation, microwaves, from mirrors, not through lenses. So they have certain advantages, primarily that they can see much finer detailed signals in the microwave polarization. And without that ability, we would not have been able to make the first detection of a different kind of polarization signal that had never really been seen before around the same time as the BICEP announcement. It wasn't as big a deal. It's called gravitational lensing, which is indicative of the presence of dark matter in the universe, which has been detected and known for a very long time. Interestingly, it has not won a Nobel Prize, unlike dark energy. But the dark matter signal was the first kind of record for the field, and us detecting it was very important step forward progress in the field. And that could only be done by a telescope about 10 times bigger than BICEP. So that telescope was 3.5 meters in diameter. And then we upgraded to 3 of those. That was the Simons array. And now we've gone back to the refracting telescopes with Simons Observatory, realizing that they actually have very significant advantages over the reflecting telescopes. And we've built 3 of them so far in Chile. They started taking data last year in 2024, and have already gotten just exquisitely incredible data. I wish I could share with you and your audience, but I can't. But it will be coming out soon. It'll be made public soon. So we have 3 telescopes that are much, much bigger than BICEP, but still much, much smaller than the Simons array. And there's 3 of them. And the reason you need 3 of them is because each one has the ability to measure not only the polarization, but also the frequency spectrum of the microwaves. And that could tell us, unlike BICEP 2, that could tell us if we're seeing dust or if we're seeing the birth pangs of the Big Bang. And that's an extremely important distinction that BICEP 1, or BICEP 2, which is the one that made the announcement, the second generation of BICEP, did not have. They could only see one color, one type of microwave. And in the Simons Observatory, we are able to see 6 different frequencies simultaneously. And that gives us a huge ability to kind of prevent us from sort of fooling ourselves that we're seeing the Big Bang's origin, if you will, the singularity version of inflation in the event that we do detect it. And there's no guarantee that we will, but at least we can measure both the dust signal that flummoxed us before and also the potential existence of the inflationary signal, which would not only sort of demonstrate that inflation took place, not only detect gravitational waves, but also very many people believe would detect the multiverse. So we're basically building a multiverse detector, which is quite astonishing that human beings are capable of doing. And another reason why I reject this notion of we're insignificant, we're just these hairless monkeys on a spinning rock. There's something magical, unique, mysterious, miraculous even about the fact that we can contemplate, let alone build technology and tools to peer back the veil on the cosmos 13.8 billion years ago.
Well, I'm excited to see the data when you finally release it. No pressure. The BICEP experiment.
You'll be the second to know.
Thank you. You know what? That's higher than I expected. The BICEP experiments landed you in the midst of some drama, to put it mildly, involving this very little known prize known as the Nobel Prize. And there's a scene in the movie A Few Good Men where Colonel Jessup says to Lieutenant Caffey that you want me on that wall, you need me on that wall. And in your book, Losing the Nobel Prize, you say that I've often felt that lay people want to know that Nobel laureates exist more than they really want to know why they won the prize. It's almost as if society sleeps better collectively, knowing that such geniuses exist. Perhaps if only to desist from doing the work themselves. It's a form of absolution and comfort to some to think, well, so-and-so may be a physics nerd, but they were lucky. They had some unfair advantage, genetic, birthright, status, or otherwise that I do not have. And Nietzsche had said something similar when he had said that thus our vanity, our self-love promotes the cult of the genius, for only if you think of him as being very remote from us, as a miraculum, does he not aggrieve us. Genius too does nothing but learn first how to lay bricks and then how to build, and continually seek for material and continually form itself around it. Every activity of man is amazingly complicated, not only that of the genius, but none is a miracle. I want to deconstruct this image of the genius with you. Over time, people are starting to realize how this idea of a genius is very idealized, very romantic. It's not reasonable. This lone genius myth is starting to get debunked. You often say that no scientist arrives alone in Stockholm. Why do you think, as a society, we have this inherent need to place people on a pedestal, elevate them, and label them as geniuses?
Well, it's a natural human urge to have, somebody that we can offload our maybe frustrations and inabilities to do things. As I say, that movie is very powerful, that scene in the movie, because, I don't have the courage to be, I have a brother-in-law who did, but I don't have the courage to, go sit and hold a gun and protect the country necessarily. or the ability physically, mentally. And so from my perspective, it's sort of comforting that such people do exist. I consider physicists, sort of the SEAL Team 6 of intellectual, kind of abilities, and that we should have people like that. We should have a cadre of individuals who can do no wrong, or can help to really parse the universe in a way that we're no longer able to do on an individual basis if we're trying to pay the rent, or take care of our kids. And these are very important and pressing things that we do need to take care of. But it sometimes doesn't give us the intellectual freedom or the flexibility to explore the things that we did maybe in college. A lot of people leave off. That's college. That's the last time they really get to, make these intellectual flights of fancy. And I think it's natural, but it's also sad, because I would love for, more people to be able to explore what makes us, as I said, uniquely human and wonderfully so. So I think these are, sort of the main things that keep me going, and to think about, can I play a role in the generation of new knowledge? And can I instruct young people to take on that, wall and sit on that wall and take care of this precious jewel of the world, which I think, this collective consciousness that we have, and this ability to really uniquely, as we know it, there's no, dolphins are pretty smart, but they're not building microwave telescopes. And so we need to take care of dolphins and so forth, but we do need to also do what we do uniquely well. And I think there is something wonderful about the Nobel, Prize winners. The process, on the other hand, is somewhat corrupted from what Alfred Nobel originally wanted. And that was sort of the partial motivation. I mean, it's a memoir more than it is, a book about Nobel Prizes. And it's a cosmological memoir. It's sort of my journey through the universe as a young person aspiring to win the greatest honor, as somebody might aspire to win an Oscar or a gold medal at the Olympics. And the pressure on what we do as scientists is every bit as great as, actors and actresses. In fact, it might be even greater, because, I just watched the Golden Globes, or I think it was the Golden Globes with my wife, who was really into acting. And there's like 10,000 categories, best costume design in a comedy. There's best adaptation of an animated. It's just like mind numbing. I couldn't stay. I had to turn it off eventually. But I can see the appeal. There's only 3 people which is not what Alfred Nobel wanted. But anyway, there are 3 people at most who can win a prize in physics every year. And there's only 5 prizes that he originally authorized. So from this perspective, these people are, tens and hundreds of times more elite than even these actors. It'll be as if, again, they had just one award ceremony, only 3 people won across the entirety of all of Hollywood, or the Olympics. The Olympics, thousands of different, people win Olympic medals, teams win it, unlike the Nobel Prize, where teams cannot win it. So my goal was to, sort of portray what it's like to aspire to be the greatest in your field, to come up short. Most people don't win Oscars, gold medals, or Nobel Prizes. So you are more likely to deal, it's a bigger audience for me to pander to, not to appeal to say, the people that don't win it, rather than write a book for the, 200 living, actually, I don't even think it's that high, 200 living Nobel laureates in all of science, not just physics, so chemistry, medicine, and physics. And that was a great, kind of honor for me to be able to portray it. I don't think anyone's ever done it that way. But most of it's about what it feels like to do science at the highest levels with the highest, most prestigious universities, and quite frankly, come up short, but not allow that to destroy me, and kind of in a stoic way to reevaluate and reassess and do better next time. And I think we are going to do that with the Simons Observatory. No means is there a guarantee we'll be successful, quote unquote, which would mean, detecting these waves of gravity, because we don't know if they even exist. We don't know if the universe had this singular origin. And that's part of the pleasure of being paid to find these things out.
Can I ask you to both steelman and strawman the case for a Nobel Prize? I know you list this out in your book completely. George Bernard Shaw, the winner of the Nobel Prize, had once said that I can forgive Alfred Nobel for having invented the dynamite, but only a fiend in human form would have invented the Nobel Prize. What are some of the good aspects worth preserving? What are some of the bad aspects at the moment? And how do you propose we fix this problem?
So part of my mission, I'm Jewish, and part of my mission was to sort of like look at it as a will, which it was. Now Alfred Nobel bequeathed this will. And in my religion, there's no higher kind of mitzvah, which doesn't mean a good deed. It means an obligation. There's no greater commandment, is what it means, than to adhere to the wishes of the dead. So if somebody dies and they name you the executor of their will, that's an extremely awesome responsibility, because there's no way they're going to pay you back. They're gone. So it's a very selfless thing. You get almost nothing from it. And so I looked at it from the context of that perspective. Could I act and kind of guess, what did Alfred Nobel want? Well, I didn't have to guess. He wrote it very clearly. He said the Nobel Prize should be given to the one person, the man, basically the person that did the greatest, conferred the greatest benefit on humanity in the preceding year from their invention in physics. Very clear. One person last year and the greatest benefit to mankind. And he died in 1896. And the Nobel Prize started getting awarded in 1901. And immediately they started to give it away to, things that had no benefit, or perhaps the benefit was unclear, give it to groups of people, give it away, in context of things that happened decades earlier. But really what, the emblematic Nobel Prize was, the first one in physics, was for the invention of the X-ray, which had occurred basically the year right before Alfred Nobel died. And it's probably pretty obvious to me, at least, that that's what he had in mind. Something that was technological, that was based on laws of physics, that revealed new pathways forward, that benefited humanity, as X-rays do, and continue to do 125 years later, 4 years later. So that was clear to me. So then now we give it to three people. We can give it to people that have died. We can give it to people that, all these sorts of rules that have been imposed upon it. Multiple people, people done long ago, things that have no benefit to humanity as a whole, like the lighthouse, these gas accumulators, I mentioned in the book. Well, Einstein didn't win the Nobel Prize, for many years after this, but this guy, Gustav Dalén, won the Nobel Prize for a type of lighthouse and buoy gas regulation system. So, how does that benefit humanity? So they obviously did it, and there are a lot of political reasons that they did it. But there are many, many worse examples than in physics in the peace prizes, but we won't get into that. And so I think that the worst, putting them up. I don't know if it's straw man or steel man. I'll say a straw man to say how much damage they can do, not only because they don't adhere to what this great person, Alfred Nobel, wanted. He had no kids, no wife, no heirs. So this is his lasting legacy, and it's clear what he wanted to do, and they're not doing it. They're doing stuff to benefit themselves, such as make new prizes and name it after him and use his fame, which his own family didn't like, in the case of the economics prize. So anyway, so those are all the bad things. I think the worst thing about it from an actual, not from a human perspective, I think there are cruel aspects about it, like not more than 3 people can win it. So a team that has 4 people on it, well, someone's going to get kicked off the island. And so that's cruel. And in the case of huge teams like LIGO or Large Hadron Collider, there are thousands of people that could have deserved it and didn't win. None of the experimentalists who detected it won. It's quite cruel. But it also distorts history, because it makes it seem like everything in science gets done, and then only the good science gets rewarded with Nobel Prizes. And if you don't have one, you're not a good scientist. So those are bad, kind of straw mans against it. Steel man it inspires people to the extent that anyone cares about science nowadays. I just watched Jeopardy last night with my kids, and there's a question about recent science Nobel Prizes. They didn't have on there, recent papers in the physical review, or Nature. They only had Nobel Prizes in physics. And so why is that? They didn't have the Breakthrough Prize. They didn't have the Templeton Prize. There are other prizes, but they're exponentially less prestigious and known about. So I think for those reasons, it does inspire the public. It's some of their only contact with scientists and science itself. I think that's very positive. It inspired me as a young scientist. I wanted to win it desperately. My feelings have obviously evolved, but and it can do a lot of good, but it has the danger of canonizing, sanctifying not only science but scientists, and I think that's somewhat anathema to the way that actual science is done.
I found your book, Losing the Nobel Prize, very illuminating. To a layperson, the Nobel Prize is such an inspirational prize. It's the top echelon of research and science. But
Absolutely, yeah.
You were very good at highlighting the problems with it and how it's not completely representative of the science that's being done. I really appreciate it. Let's start closing out with some quick rapid fire questions. What are some books, movies, role models that have strongly influenced you?
Well, books and role models, it's pretty easy. A lot of the books that inspired me as a young person were books by actual scientists that did, groundbreaking work. Books by Carl Sagan, as I mentioned. I tried to read early books by Einstein. That was very difficult. Einstein's not as good a writer, it turns out, as most people come off thinking that he is. And then, of course, Galileo is my real intellectual hero because he was so gifted, such a brilliant genius. He was a theorist. He made up theories and hypotheses. Many credit him with the creation of the scientific method, at least in the West. But he was also an experimentalist. He built telescopes. He improved them. He built early computers and timekeeping devices. You have to remember, there was no such thing as a clock back then, 400 years ago. So what he did, and he was a beautiful writer. And so because of that, I'd wanted to, a lot of the stuff I consume nowadays is in audio because I can consume it at 2x speed. But I found that there was no book by Galileo in audio form, so I couldn't do that. So I made it with my colleagues Carlo Rovelli, Lucio Piccirillo, and others. And so we made the first ever audiobook, and it's on Audible, Kindle, or not Kindle, Amazon, wherever you get audiobooks. And that was a great thrill for me. So yeah, I would say those are my scientific heroes.
In your book, Into the Impossible, and on your podcast, you have this recurring question where you ask guests, what is one piece of advice you would give a younger self? So I want to flip the same question onto you and ask you today, what advice would you give to your younger self?
Yeah, for me, it's pretty easy. I think for a long time, I venerated Nobel Prize winners and the scientists who won it. And they're really just like normal people. A lot of them are. And I think that's been the most kind of revealing thing. I've spoken to 21 Nobel Prize winners on my podcast. And it's always, clear to me that they're normal people with normal desires. And I think for a long time, especially as a kid and even as a young scientist in my 20s and early 30s, I just wanted that kind of stamp of approval, that seal of approval for many reasons, but that I get into in my first book. But the main thing was to not really venerate that, to really don't try to impress, 300 mostly, men in Sweden. Try to impress yourself. Try to, be the person that your 10-year-old, 12-year-old, 15-year-old self would really look up to. And that involves many, many other things. A lot of these men and women who win it are not great role models, unfortunately. And neither was Einstein or he was a horrible father. Feynman was a terrible, person in a lot of ways to his students and to women especially. So you don't want to emulate, you don't want to venerate anybody. And I think that was the real exorcism for me was realizing it's not a God. These people are just like me, no better, no worse. And I can be, maybe not achieve what they achieve, but realizing that I can have the best character of anybody. And that's something I can actually control.
Great advice. I'll stop going for the Nobel Prize. I've taken your advice. Last 3 rapid fire questions for you. In the mid-90s, the sports psychologist Robert Goldman posed the Goldman's dilemma, where he proposed to elite athletes that if they were offered a drug that would guarantee them an Olympic gold medal, but they would lose their life in the next 5 years, would they take that drug? And almost half the athletes said yes. So I want to pose an analogous question to you. Is there any one cosmological mystery that you would like to get the answer to that you're willing to trade your life for?
No, absolutely not. I mean, the thing is, a lot of those athletes that do it, they're very young. They don't have kids. They don't have a family. No, they're I've come to be less greedy, in that I don't necessarily need to have scientific answers answered in my lifetime, but I do have to have my kind of values and the things that I consider valuable passed on to my children, my spouse and I, to our children and hopefully their children and beyond. So that's much more important to me. So there's no way I'd trade even a couple of minutes for a Nobel Prize or for a discovery. And if it's meant to be, it's meant to be.
Meant to be. Last 2 questions. What would you like your legacy to be?
I think the main legacy for me is, again, it comes back to my family. There's nothing greater that a person can create. By the way, you don't have to have your own kids. You can influence and be an ideological heir, a father, mother, however you want to be, to a host of people. You don't have to have biological children. I'm blessed to have them, my wife and I, and I'm blessed to have a good partner. And to me, it's the hardest job possible. I mean, it makes being a scientist, just like, again, I feel like I get paid, to be like an ice cream taster. That's kind of the way I always felt like, who's going to pay me to do this? I literally never thought it was possible to be a professional astronomer. I mean, it's insane. My hobbies, like on a clear night, I'll go out with my sons, my daughters, I'll look at the stars. It's like my hobby is my profession. It's incredible. It's like, it's such a blessing. So no, I mean, for me, that's the greatest legacy, is communicating curiosity to hopefully millions of people. And I know that I've impacted millions of people because I hear from them all the time, both good and bad. You're really stupid, and you made them, like, how can you do this? And how can you say that? But other people are like, you changed my life. And being able to do that. And I would say, the legacy of communicating what scientists discover, never dumbing it down, never assuming the audience is stupid, and really just bring them in, because at the end of the day, the public pays my salary, and I have to be aware of that. And it's a great privilege, and it's a great responsibility.
We started this conversation talking about your penchant for these big existential questions, these impossible questions in a way. And for the final question, I just want you to relax. I don't want to add more to your plate. I want to just pose the easy question to you, possibly the easiest question of all time. What is the meaning of life, Brian Keating?
Yes, it is very easy. There's a phone ring. I got to go to get the phone. No, I'm just kidding. I think the meaning of life, I've said this, Lex Friedman and Jordan Peterson and Joe Rogan and recently Andrew Huberman. The meaning of life to me is to do those things which, if they were taken away from you, would devastate you. Meaning that if you have something that you can't live without, that's very important. That is something that is just like, I could live without my iPhone. I live without it I'm probably addicted to it, but I live without it for, 40 years, 30 years. I don't need it to survive. It would be painful. I wouldn't like it, but it's part of this, kind of stoic concept called memento mori. Just remember you're going to die. And, from my perspective, the thing that would bother me is not, being scared to die. I mean, I've accomplished a great deal. I'm not scared to die. I don't feel like, well, I've wasted my life or, by any means. It would be that I would, my children, my friends, my community, my faith network, whatever, that they would, that would be the end, because it's very hard to imagine, many, many generations from now, people still, reading my books and so forth, listening to my podcast. So it's really doing those things, which if I didn't have my community, if I didn't have my friends, if I didn't have my spouse, et cetera, that would devastate me. So I invert that. It's kind of like an anti-bucket list, like things I don't want to do rather than things I do want to do. I've done a lot of things I want to do. I don't have many things. I don't want to go to the moon. I don't want to go to Mars. I don't want to have like a mega yacht or a fleet of rockets or own a social media company. I don't want to do any of those things. I like my life as it is right now. And so therefore, if one of those major key components of family, friends, faith, etc., if those were to be taken away, it would be devastating. So lean into those things, do more of those things, find more of those things, exercise, volunteering, all those things. They can be part of your identity, and you were to be forbidden by law to do them, you would be devastated. That's a signal you need to do more of that, and that's your personal meaning of life.
I think that's a great approach. Professor, if people want to connect with you, find out more about you, read your books, listen to your podcast, what is the best way to find you?
Oh, I'm everywhere. You can't avoid me. To resist is futile. My website, briankeating.com. Join the mailing list, though. Seriously, I do send out really cool, and I think it's cool. I think it's fun. I go, tens of thousands of people get it and don't, I don't charge at all. I don't really feel the need to do that. You will win a meteorite if you have a .edu email address. That's briankeating.com/edu, and you live in the US. I'd love to connect with more people. That's where I share like a little bit longer form stuff. The podcast, sometimes I'll do audio essays on, but this year, a lot of cool stuff is coming up with some really just spectacular interviews that I got keyed up. And then in the science realm, I'm going to keep you all, up to date with what we're doing, the various telescopes, but also with some of my competitors and colleagues from around the world. So I think it's a unique kind of exposure. So that's the mailing list that you hopefully folks can subscribe to.
I highly encourage people to join the mailing list. Professor, thank you so much for this conversation. It was fantastic. It was an honor for me. Thank you.
Yeah, it was a great use of my time. I can't congratulate you enough on how much you've done and your success. I'm really happy and proud of you.